Welcome to Homework Lib.
So over here in this problem, we're given two positive charges, Q1 and Q2, given the different positions R3, and this overall distance R, so we can calculate the distance in between Q2 and A that we're going to call R1. And we're told that given the information of all of the distances on the system, we have a point charge Q that is going to be released from rest, and we want to know what is going to be the speed of the particle when it passes through this point. So for this, let's remember that we can employ conservation of energy, which tells us that the change of kinetic energy plus the change of electric potential energy, which is often labeled as U, needs to be equal to zero. Or written in another way, the initial kinetic energy plus the initial electric potential energy is going to be equal to the final kinetic energy plus the final electric potential energy. In this case, we're told that the particle is going to be released from rest, so then that means that the initial kinetic energy is going to be zero. So the final kinetic energy is going to be equal to minus the change of electric potential energy. And this is going to be equal to 1/2 mass velocity squared. So recall that the definition for electric potential energy is going to be equal to Q times V. And in this case, if we are dealing with changes of electric potential energy, this is going to be Q times delta of the potential. Thus, in order to calculate the velocity for this problem, what we require is the potential at this point, the initial potential, and the final potential, which is at point A. So we need to find both of those potentials. Remember that the electric potential, Vi, is going to be equal to K times, being K the Coulomb's constant, times the charge divided by the distance that separates both of them. So, in this case, for the initial potential, this is going to be equal to K times Q1 divided by the distance in between Q1 and the origin, which is going to be this point, plus K times Q2 divided by the distance in between the origin and Q2. In this case, this is going to be R2 directly. The first one is going to be a, a right triangle. Let me try to make it as straight as possible. Something like this, which is going to have a distance equal to the square root of R squared plus R2 squared by Pythagoras theorem. So the initial potential is going to be equal to, I'm going to factorize directly the value for Coulomb's constant just to make it easier for all the calculations. Q1 divided by a square root of R squared plus R2 squared plus Q2 divided by R2 squared. Sorry, by R2 directly. So replacing the values, this is going to be 8.99 times 10 to the 9 Newton meter squared Coulomb squared multiplied by the value for Q1, which is 37.91 millicoulombs. We're going to replace the milli by times 10 to the minus 3 divided by the distance, which after doing these operations is going to be 43.257 centimeters. So we need to transform this into meters. 2567 times 10 to the minus 2 meters plus the value for Q2, that is, in this case, 87.23 times 10 to the minus 3 coulomb times 10 to the minus 3 coulomb divided by the distance that we're going to have, which is 28.94 centimeters, which is 28.94 times 10 to the minus 2 meters. So my initial potential is equal to 3.4976 times 10 to the 9, and the units are going to be Newton meter per coulomb, which is the same as joule per coulomb, which is the same as volt. And now the final potential at point A is going to be equal to kQ1 divided by the distance from Q1 to A, which is R3, divided by R3, plus Q2, kQ2 divided by the distance, R3, not R cubed, just to make the difference, times the distance that we got here. That would be R1. Remember that R1 is nothing but R minus R3, so this would be 13.15 minus 9.645, which is 22.505 centimeters. Okay, so with this, now becomes, let's factorize again Coulomb constant, 8.99 times 10 to the 9 Newton meter cubed Coulomb squared times Q1, which is 37.91 times 10 to the minus 3 coulombs due to the milli being in front of it. R3, that is 9.645 centimeters, which corresponds to 10 to the minus 2 meters, plus 87.23 times 10 to the minus 3 coulombs divided by the distance of R1 that we set, that was equal to 22.505 times 10 to the minus 2 meters. So with this, the final potential is equal to, which is going to give us 7.0018 0181 times 10 to the 9 volts. Thus, the change of potential, which is final minus initial, would be equal to 3.5205 times 10 to the 9 volts. And this is the value that we're going to plug in into our formula from above. So we know that the change of potential is equal to Q times delta B, and that the final kinetic energy is going to be equal to minus Q times delta B, according to this equation over here, right? So we can directly put 1/2 of mass velocity squared is going to be equal to minus Q times delta B. Thus, velocity squared would be 2 times Q delta B with the minus in front of it divided by M. We can get rid of the square root and take the square root on both sides. So the final velocity that we're going to have is going to be equal to a square root of minus 2 times the charge that we added, which is minus 6.551 microcoulombs. Remember that micro corresponds to times 10 to the minus 6 coulombs, times the change of potential that we got as 3.5205 times 10 to the 9 volts, or which would be the same, joules per coulomb, as we saw here, divided by the mass, which is 26.31 grams. In this case, we need to transform this into kilograms, correct? So 26.31 grams. We know that 1 kilogram corresponds to 1,000 grams. This is the same as doing the times 10 to the minus 3 factor. So the final velocity would be equal to 1,324.07 meters per second. You can verify the units. Remember that joule is nothing but Newton times meter, which is kilogram meter squared divided by second squared. So kilogram cancels out with kilogram. We end up with meter squared over second squared. So the square root of that is what gives us our result. So just for simplifying this, grams with grams, and joules is kilogram meter squared over second squared. So we replace this, kilogram and kilogram cancel out, so we end up with meters per second. However, that really doesn't matter. As long as you keep everything in the International System of Units, you're going to get the correct result, which is this one over here. So with that, it would be all. Just as a recap, we employ conservation of energy. We need to find the initial potential and the final potential. The difference of the potential is going to give us the change of potential energy for the system. And since the particle started at rest, the initial kinetic was equal to zero. So we can follow this procedure with the numbers over here, and we get solving for the final velocity coming from this equation. So with that, it would be all. Thank you very much and have a good one.